Wanted to describe a problem that involves Faraday's law and involves a moving circuit. So in this case, we got a circuit that comprises a resistor over here on the left, two rails, one upstairs here and one downstairs here, and a moving rod vertically here. And in this problem, the rod is moving at constant velocity towards the right. So in this case, because the arrangement is immersed in a magnetic field, a perpendicular magnetic field to the circuit, there's going to be a changing magnetic flux through the circuit. As the rod rolls to the right, then the number of field lines passing through the circuit is going to grow. Therefore, the magnetic flux is going to grow. So there's going to be an induced current and there's going to be an induced EMF. Now, what we're told is the induced current. It's 1 amp. That current is caused by an induced electromotive force. And that induced electromotive force is caused by the changing flux, changing magnetic flux that was caused by the fact that the rod is rolling, moving from the left to the right. So through that chain, we can relate the known electrical current to the velocity or the speed of the moving rod. And that's how we're going to start this problem. So in this particular problem, we're actually asked to work out a number of things. We're asked to figure out the speed of the moving constant motion rod. We're asked to figure out the force that we have to apply to move that rod at that constant speed. We're asked to figure out the power that we supply to the circuit by exerting that force. And we're also asked to figure out the power that's dissipated by the resistor due to the current flowing through the resistor. So there's a whole series of interesting questions there. The things that we're told are the current that was induced in the circuit. So that's very important. And then we're told some facts about the circuit and the field. So we're told the strength of the field is 2.5 Teslas. We're told that the resistance of the resistor is 6 ohms. And we're told that the length of that moving rod is 1.2 meters. All that information we need to relate the induced current that's flowing in the circuit to the motion of the rod that's causing the induced current in the circuit. So the first thing I'm going to do is solve for the velocity of the moving rod. Again, the way we're going to find V is by starting with the known induced current, or 1 amp. That tells us that there's an induced EMF in the circuit to drive that current. That tells us that there's a changing flux, magnetic flux through the circuit to create that induced EMF. And that changing flux is related to the speed, V, of the rolling rod. For example, supposing the rod wasn't moving, there would be no induced current or EMF or changing flux in the circuit. So let's follow that chain. So I, the induced current, is going to be, by Ohm's law, the induced EMF divided by the resistance of the resistor. In turn, by Faraday's law, that induced EMF, that's the rate of change of the magnetic flux through the circuit, as delta phi, delta t, the change in flux divided by the change in time. And in turn, when you have a changing flux due to a moving circuit or a moving component of a circuit, that change in flux in this situation can be written as that rate of change of flux can be written as B times L times V. This equation makes sense if you think about it. So it says that the faster the rod moves, then the greater the rate of change of flux. It says that the longer the rod, then the greater the rate of change of flux. And it says the greater the field, the greater the rate of change of flux. All those things make physical sense. But if you look at this equation, look at this relationship, we can rearrange it for the unknown speed in terms of the known current. So it will just be IR divided by BL. And then we can feed in the values of I, R, B, and L. So we got 1 amp for the current. We got 6 ohms for the resistance. We've got 2.5 Teslas for the field. And finally, we got a length of the rod that's 1.2 meters. And if we calculate that, I got 2 meters per second. So that's the speed of the moving rod. And it was really figured out by understanding that the induced current came from an induced EMF, which came from a changing flux, and how that changing flux is connected to the speed, the motion of the rolling rod. What about the force? The force that we're pushing on this rod to move it from left to right. Firstly, it's important to recognize you will need a force. There is a current that's flowing through this rod, the induced current, and that's a current flowing through that's a current flowing in a magnetic field, the field that the circuit's immersed in, and that will create a magnetic force. And we're going to need to apply our own force to overcome the magnetic force and keep the rod rolling at constant velocity. So let me sketch that in a little bit more detail here. Let's start by figuring out the direction of the magnetic force on the rolling rod, and then we can see the direction of our force on the rolling rod that's needed to overcome that magnetic force. So which direction is the current flowing in this circuit? Which direction is the induced current flowing in this circuit? Well, the rule for that is that the induced current will create an induced magnetic field that will oppose, that will try and cancel out the change in magnetic flux. So as the rod rolls towards the right, there's more flux into the screen. There's more field lines enclosed in the circuit that are going into the screen. So the induced current will try and create a magnetic field out of the screen. And so if we want to make an induced current out of the screen for this circuit, this loop, then we can use one of our right-hand rules. It says if we point our finger in the direction of the field that we want, which is out of the screen, then our fingers will curl in the direction of the current. And they curl, my fingers are curling, my fingers of my right hand are curling counterclockwise. So the current is flowing upwards on this moving rod. So that current is immersed in a magnetic field. And those are the ingredients for a magnetic force. And so next step, let's figure out the direction of the magnetic force. The magnetic force is given by another right-hand rule. It's the right-hand rule for the field equation, magnetic field equation. That's the one that says that you take the palm of your hand and you point it in the direction of the current, so up the screen. You curl your fingers in the direction of the magnetic field, so that's into the screen. And then your thumb will point in the direction of the magnetic force. And so that's, my thumb is pointing towards the left. So over here in magenta, we've got a magnetic force, I call it FB, that's pointing towards the left-hand side. And so that's why we have to apply an equal-sized opposite force of our own I'll just call it F, towards the right-hand side to counteract the magnetic force and to move that rod at constant velocity. So there's quite a bit of understanding that went into that. The fact that we've got a current that's flowing counterclockwise, and that was kind of Lenz's law. The fact that we've got a magnetic force through the magnetic field equation, because we've got a current in a magnetic field. And finally, the fact that that means we need to ourselves apply a force to move the rod from the left towards the right at constant velocity. Now we've got that picture, it's actually pretty easy to figure out the size of the force that we're applying. So how big a force are we applying? See if we can figure that out. So the size of the force that we're applying is equal to the size of the magnetic field force, so FB, and that force due to the magnetic field by the magnetic field equation is just actually going to be BIL, the field strength times the current times the length of the rod. I don't have a sine theta because sine theta in this case is sine of 90 degrees, which is just a 1. That's because the magnetic field is perpendicular to the current. The field we know, the current we know, the length of the rod we know, so we've got all the ingredients to calculate the force. Let's just go ahead and calculate it. 2.5 Teslas is the field strength, 1 amp is the current, and then finally 1.2 meters is the length of the rod. If you multiply those together, I got 3 newtons. So that's the size of the magnetic force, and it's the size of my force as I push the rod from the left towards the right. They're equal-sized, opposite directions. Finally, we're going to calculate the power that is supplied by my force. So I'm going to write that just P. That's the power that's supplied by my force. No, maybe I'll put a subscript F on it, by my force. And we're also going to calculate the power that's dissipated in the resistor. I'm going to call that P, power, with subscript R for resistor. So one of these powers is energy being supplied to the circuit, that's by me, and the other one is energy being dissipated into heat by the circuit, that's by the resistor. So we want to find both of these, and we're going to be interested in comparing them. So for the power that I supply with my force, well, my force supplies energy, supplies power to the circuit, and the size of the magnitude of that power that I'm supplying is simply, this is an equation from 2 to 11, is simply the product of the force that I'm applying times the speed of that rolling rod. So this is an equation for power supplied. It's a little like the energy is force times distance, the power is force times speed, because power is the rate of transfer of energy. Anyway, we know the force. It was 3 newtons. We just calculated it. We know the velocity of the moving rod. That was 2 meters per second. And so the power delivered is 6 joules per second, 6 watts. So that's the power I'm supplying. Every second I supply 6 joules. What about the power dissipated in the resistor? So that we call PR. And when current flows through a resistor, when a voltage is applied across a resistor, there is power dissipated in the resistor. It's power that goes into thermal energy, into heat. The resistor gets hot. And there are several ways you can write that. You can write it as the current times the voltage across the resistor. You can write it as in terms of the voltage and the resistance, or you can write it in terms of the current and the resistance. And that's the handy one here. We're going to write it as I squared R the current was 1 amp, the resistance was 6 ohms, and if we multiply this out, we get 6 watts of power dissipated. And that's important, actually, our result here. The power I'm supplying to the circuit is equal to the power that's being dissipated by the circuit. So I can't create energy or destroy energy. The energy will just flow through the circuit. And we see it here flowing through the circuit. From me, I'm putting energy into the circuit, kind of like a battery puts energy into the circuit, and then it's being dissipated. It's being turned into heat in the resistor. And so I'm putting in 6 watts and the resistor is dissipating 6 watts. Anyway, let me finish there. That was an example problem, example question that involved induced currents, induced EMFs, and Faraday's law that describes induced EMFs and induced currents. A particular feature of this problem was that the induced current, induced EMF, was not due to a changing magnetic field. The magnetic field was uniform in time, and it wasn't changing in space. The magnetic flux change in this particular problem was due to the circuit, the shape of the circuit, the dimensions of the circuit changing in time. So for the rate of change of magnetic flux in this problem, we use that equation BLV. That was very important here. Anyway, once we understood that, we could relate the induced current, which is sort of the effect of induction, to the motion, the speed v that caused the induction. And then we could, by just thinking of magnetism and currents in magnetic fields and magnetic forces, we could figure the force needed to push the rod and the energy or the power that's supplied in pushing the rod through that magnetic field. So that those latter two parts were really just about magnetic fields, electrical currents, and magnetic forces.